All right, welcome to The Explainer. Today we are diving straight into a seriously fascinating side of artificial intelligence. We're talking about how machines process the gray areas of information. We're going to literally follow the exact journey of a single piece of data as it travels through what's known as a fuzzy inference system. So let's just jump right in and see how computers actually handle a world that, well, isn't perfectly black and white. Here is our quick roadmap for this explainer. We'll start with an intro to fuzzy inference. Walk through the 4 strict steps of the process, look at mapping rules with FAM, check out 3 popular fuzzy models, and wrap up with developing and tuning these systems. Let's get to it. Okay, kicking things off with Section 1, Intro to Fuzzy Inference. Before we get into the really complex systems, we have to ask, what does it actually mean for a computer to process information that isn't perfectly crisp?
Well, as a quick refresher, fuzzy logic computes based on degrees of truth. Think about it. It allows our systems to handle imprecise or even incomplete data and to model highly complex, non-linear functions. Instead of forcing a piece of information to belong entirely to a category, or not at all, fuzzy logic lets an element belong to a set just partially. It's a real game changer.
To put that into perspective, let's compare it to traditional Boolean logic. In Boolean logic, variables are sharply defined, right? They are discrete values, exactly 0 or exactly 1. You're either in the club or you're out, no in between. But with fuzzy logic, variables are lexically imprecise. They can hold literally any real value between 0 and 1. It's just a much more natural, incredibly expressive way to represent the real world. In fact, it lets just one fuzzy rule replace a whole bunch of rigid conventional rules.
With that baseline set, let's move into Section 2. The 4 steps of fuzzy inference. We are going to trace the exact journey of a single input right through the standard Mamani-style process.
This journey follows a really strict sequence to derive a conclusion from an input. First up is Step 1, fuzzification. That's finding the degree of membership. Then we hit Step 2, rule evaluation, where the system actually applies those truths. Step 3 is aggregation, pulling it all together. Until finally, Step 4, defuzzification, translates everything back into a crisp, real-world number.
Now, focus on how the input interacts with those if antecedents in Step 2. That truth value literally slices the then consequent. This is known as clipping, or, if you want the technical term, max-min composition. We essentially shear the top right off the curve, leaving us with a flat-topped shaded area.
But, clipping isn't the only way to do this. We actually have a choice between clipping and scaling. Clipping, as we saw, cuts the top off. Sure, it loses a bit of information, but the reason we care is that it involves much less complex math. It creates a shape that is way faster and easier to defuzzify later. Scaling, on the other hand, adjusts the original membership function by multiplying its degrees by the truth value. This preserves the original shape of the fuzzy set, and that is absolutely vital when preserving information is critical to the accuracy of your expert system.
Let's fast forward past Step 3, where we combine all those shapes together and arrive at Step 4, defuzzification. Because while fuzziness is great for evaluating rules, a machine ultimately needs a crisp, hard number to actually take action, right? The most popular method for this is the centroid technique. Think of it as mathematically finding the exact center of gravity. It finds the precise point that slices that unified fuzzy shape into 2 perfectly equal masses. And boom, that center point becomes our final, definitive output number.
Which brings us right to Section 3, mapping rules with FAM. We know how the rules are evaluated now, but how is the brain of this entire system actually organized?
Well, designers use a fuzzy associative memory matrix, or FAM for short. It's really cool how this grid visually encodes the relationship. The input fuzzy sets sit right on the axis, mapping directly to the output consequence inside the boxes. By structuring the knowledge in this grid format, multiple inputs can be combined with logical conjunctions. It basically makes complex human knowledge incredibly easy to visualize and evaluate.
All right, let's explore Section 4, 3 popular fuzzy models. The standard Mamdani process we just looked at is great, but there are alternative models that handle that then part of the rule and the defuzzification very, very differently.
First up is the Mamdani fuzzy model, introduced way back in 1975. This is the widely accepted standard we've been exploring. It produces a 2-dimensional fuzzy set as the output of each rule. And because it describes expertise in such a human-like manner, it's incredibly popular. But there's a catch. Finding the exact center of gravity for all those 2D shapes, it is computationally heavy. Like really heavy.
So, what if we need speed?
Enter the Sugeno, or TSK fuzzy model. Michio Sugeno introduced this absolutely amazing efficiency hack. Instead of outputting a big, clunky 2D shape, the rule consequent is just a mathematical function or a constant. Visually, this creates a singleton spike. It's unity at one particular point and zero everywhere else. And because the outputs are just these simple spikes, the system can defuzzify the results almost instantly using a straightforward weighted average. It is a massive computational shortcut, making it perfect for dynamic, real-time control problems.
And then we have the Tsukamoto model. Here, the consequent is strictly monotonical, meaning it's always increasing or always decreasing. Because of this really unique shape, the Tsukamoto model calculates the overall output directly as a weighted average of each rule's output, meaning it technically skips a distinct defuzzification step entirely. No way, right? While it's a bit less transparent than Mamdani or Sugeno, it's just another fascinating way to map our inputs to outputs.
Finally, we hit the shop floor in Section 5, Developing and Tuning Systems. You've built your expert system, encoded your sets, written your rules, but what happens when it simply underperforms? Well, you have to tune it.
Think of this as your mechanics checklist for tuning a fuzzy system. You can redefine the ranges of your variables or revise the physical shapes of your sets. But here is the absolutely crucial secret: the overlap. Neighboring triangle or trapezoid bases should overlap somewhere between 25% to 50% to prevent erratic performance. You can also write what are called hedge rules to capture specific pathological edge cases, or even just adjust a multiplier weight to change how important specific rules are when they execute.
Which leaves us with a final thought to ponder. We've seen how the Mamdani model beautifully captures that human-like expert knowledge, while the Sugeno model trades that traditional fuzzy shape for a singleton spike to achieve raw, blistering computational speed. As AI systems are continually pushed to process more complex data faster than ever before, which approach do you think will ultimately dominate the future? The human-like nuance of a fuzzy shape, or the real-time efficiency of a mathematical spike? Thanks so much for joining me on this explainer. I really hope this gives you a much clearer picture of exactly how machines navigate the gray areas.